So today we will discuss about microbial death kinetics. So microbial death kinetics is a first order uh, phenomena or a first order reaction. So it means the final number of microorganism after the thermal treatment that directly depends on what is the initial number of the microorganism. Okay. So that can be written as, say, n is the number of microorganism, so dn divided by dt means rate of change in concentration of the microorganism with respect to time is directly proportional to initial number of microorganism or initial concentration of the microorganism. Okay. So we all know that when we remove this proportionality constant, we need to place a proportionality symbol. We need to place a constant here. So what I will do, I'll just write dn by dt is equal to kd and n. Okay. So here when we, this is the proportionality constant kd. Okay. This is death rate constant. Okay. D for death, k for k is constant. Okay. So we know that when we are inactivating microorganism means the number of microorganism or the concentration of the microorganism is reducing. So what we will do, we'll put a negative sign here just to express that this constant represent a negative slope. Okay, what does it mean actually? For example, if there is a growth of the microorganism, so the slope will be like this. Now this is time, this is concentration of the microorganism. So with respect to time, what is happening? Concentration of the microorganism is increasing. So this is growth, this is the slope. But what will happen in case of death? Time and this is concentration. It will be something like this. Now with respect to time, with increase in time, concentration of the microorganism will fall. So this is a negative slope. So that's what I have written, k minus k. Okay. So now we'll do the variable separation. We'll take this n to the left side and we'll take minus kd and dt to the right side. So if we integrate here, say ni is the initial number of microorganism and nf is the final number of the microorganism. Similarly, say this is 0 time to t time. Okay. So what is the integration of dn by n? That is ln n. Okay, is equal to, and your limits are ni to nf is equal to minus kd and integration of dt is t. Limits are 0 to t. So what I can write here, can I write it like this? Ln nf minus ni is equal to minus kd t minus 0. So for ln nf minus ni, we can also write it as nf by ni is equal to minus kd t. Okay. So this is the first order death kinetics equation for the microorganism. Okay. So I'll just rearrange it. How can I write it? Can I write it like this? Ni by nf is equal to, so I have reversed this, right? So what will happen? I can write kdt. This negative sign will go away. So if you want to, understand this equation in a graphical form, it will be like, see, this is your y is equal to mx plus c. C is your 0. Okay. So this is your ln ni by nf and this is your t Okay, so what will happen? Ni by nf, it is a positive slope. See, there is no negative sign here, no negative sign here. So we'll just draw a straight line. Okay, and your slope will be kd. But if you want to draw something like this, ln nf by ni, so what will happen? The slope will be -1 minus kd. Okay, so this is our final equation. I'll just rewrite once more. By nf, why ni is upside? Because ni is initially more microorganism is there. Nf is final, less microorganism. Okay, kd t. What is this t actually? So this t is nothing but your thermal death time. Okay, so can I write it like this? Ln ni by nf is equal to kd f, because we denote thermal death time with the symbol f. Okay, then there is one relationship, established relationship. Kd is equal to 2.303 divided by d. Okay, so what I will do, I'll just replace this in this equation. So this equation, the initial equation, the primary equation will become ln ni by nf is equal to, instead of kd, I'll write to 2.303 divided by d into f. Okay, so here how to convert this ln to log? Okay, if I want to represent this in the form of log, what I have to do? It is 2.303 log. Okay, so ni by nf is equal to 2.303 divided by d into f. So I can cancel out 2.303, 2.303. So this will be is equal to how much? Log ni by nf is equal to f divided by d. So this is one more equation where you can see you have initial number of the microorganism, final number of the microorganism, thermal death time and decimal reduction time. Okay, so this d is decimal reduction time. So from this equation, what you can do, if you have decimal reduction time, you can calculate rate constant. If you know the rate constant, you will be able to calculate the decimal reduction time. Okay, so I hope this is clear to everyone. So we started with how the rate of change of microorganism with respect to time is directly proportional to initial number of the microorganism. Then we integrated it and we came to the equation that ln nf by ni is equal to minus kdt. We just rearranged with the negative symbol. Okay, just we multiplied negative sign on both the side, so to have a positive slope representation. So the equation will become ln ni by nf is equal to kdt. Okay, so this way in graphical form we can represent this. Okay, so ln ni by nf is equal to kd t. Okay, so this is your thermal death time, this t is your thermal death time. Okay, so we just, what we did, we just wrote, instead of writing t, we just represented with the symbol of thermal death time. What is the symbol of thermal death time? F. Okay, then you can see here there is a established fact already available. What is that equation? That fact is kd is equal to 2.303 divided by d. So we just replace this value in this particular equation. to get ln ni by nf is equal to 2.303 divided by d into f. So then what I did, I converted this ln to log. How to do that? Ln is equal to 2.303 log value. Okay, so I just wrote that, and as a result I could able to cancel out this 2.303 and 2.303. So finally we'll be able to arrive at log ni by nf is equal to f by d. So if you have this equation, you should be able to calculate, for example, initial and final number of microorganism is given, say decimal reduction time is given, you will be able to calculate thermal death time. Say along with these two, thermal death time is given, you will be able to calculate decimal reduction time. Say thermal death time, decimal reduction time is given, okay, and say initial number of the microorganism is given, you will be able to calculate final number of the microorganism. Okay, so this way this particular equation can be used for various calculation of thermal processing. Okay, so thank you, see you.